In this video, we're going to discuss common reactions of alcohols. So first, most direct synthesis of an alcohol, how to make it. Commonly for our cases, that is going to be things like I have an alkene, I add water, and you produce an alcohol. So double bonds plus water, you hydrate them, you can end up with an alcohol. When you synthesize these, though, there are some restrictions. If I have propene and I was to add water, well, there's two options. I could have the OH attach on the end, or I could have the OH attach on the middle. Both of these actually get synthesized, but one of them is far more common, and that is the inside option. As a general rule, when you add groups across a double bond, you always put the hydrogen on the carbon that has the least carbons attached. And so that hydrogen that we had to add, well, one of these was on a carbon that had 2 carbons, and one of these was on a carbon that had only 1 carbon. As a result, the more likely option is the one that only had 1 carbon it was attached to. So if you took propene and you hydrated it to make an alcohol, you would get isopropanol. And this is how we make almost all our isopropanol. If you have any in hand sanitizers or rubbing alcohol at home, this is basically how we produce it. We get almost no 1-propanol or propan-1-ol. This is a severe problem. That's called a terminal alcohol. A terminal alcohol is extremely useful for a lot of reactions, but they're actually very difficult to make. Now, if you use ethene, you have no choice but to get a terminal alcohol, so ethanol is a pretty common one. But if you want larger butanol, butan-1-ols and the like, they are actually very difficult to synthesize. The individual who first discovered how to do it using borane won a Nobel Prize for it. Before that, we just had to get them from nature. If anybody's ever on UW campus, behind chemistry, the old Bagley building, there's a garden. The garden has all these weird fruits, winter melons and things like that. That was there because the early chemists had to grow them, purify them to collect their own reagents because you could not buy them. And they weren't advanced biomolecules. They were propanol, 1-propanols and the like. This is generally how you synthesize alcohol. What can alcohol get used for? What can we make with it? First and foremost, your alcohol can become an alkene. We just got done saying you can make an alcohol from an alkene, but any reaction you can do forward, you can do backwards. If I've got an alcohol and I heat it, basically heat it up, let it boil for a while, what'll happen is water will break off. You dehydrate. Well, a neighboring hydrogen will react with it. The two of them will leave, and you'll end up with a double bond plus water. You are just undoing the hydration. So alcohols, if heated long enough, can actually fall apart. This can lead to some problems. If you've got 1-propanol, or propan-1-ol, and you let it get hot for a while, it can form a double bond. It'll steal the hydrogen nearby, 1 carbon away. Those 2 carbons will connect to each other to make up for the bond they each lost. That leaves you some water around. If that water continues to bounce around, it could go back and react again. It could hydrate. But if that happens, it's going to prefer connecting to the top, to that inside. And so you can actually turn a very rare terminal alcohol into a non-terminal alcohol if you're not careful. This is a less common problem. Generally, our idea here is just I can take an alcohol and I can turn it into a double bond. And so alcohols can become alkenes with heat. Just heat them for a while. Additionally, your alcohol can become aldehyde or ketone. If I've got, let's say, ethanol, I have to add an oxidant. What'll happen is that oxidant is going to end up removing one of our adjacent carbon's hydrogens. And so the hydrogen that was on oxygen and one that was on its attached carbon leave. They're gone with the oxidant, and what is left is you replace that missing bond from the oxygen and the carbon with each other to get a double bond. Unfortunately, aldehydes tend to react with oxidant as well to form carboxylic acids. In fact, they are better at doing this than the alcohol is. So if you had a whole bunch of alcohol, like 100 of the alcohols, and 100 of your oxidants, and they start to react. So you have 99 alcohols, 99 oxidants, and 1 aldehyde. Well, the aldehyde will immediately steal 1 oxidant, leaving you with 99 alcohols, only 98 oxidants, 0 aldehydes, and 1 carboxylic acid. The net result is that at the very end, you'll have half your alcohol left, you'll have used all your oxidant, and you'll have everything converted to carboxylic acid. It is really hard to stop at aldehyde. There are ways to do it, but it involves talking about those oxidants. Oxidants will not be studied in this course. There are many, many oxidants. Potassium permanganates, sodium dichromates, various just O2 works. If you leave an aldehyde bottle open to dioxygen, if you just left the bottle open overnight, you come back in the morning, it's not a bottle of aldehyde anymore. Aldehydes are very reactive. Oxidants, depending on the type of oxidant you're using, some kind of chromium 6+ type or others, behave wildly different. There are hundreds of oxidants. You can get your nitric acid in there even. That's a good oxidant for things. Each of them behaves differently. Each of them does different things. Some of them have oxygens that they can stick those 2 hydrogens on. Producing water is very common. But others don't have available oxygens. And so it's very difficult to make things like carboxylic acid if you can't add an extra oxygen from somewhere. And so this second step to make the carboxylic acid actually depends on the type of oxidant. The most common ones all have available oxygens and make that happen, but there's a few that don't and allow us to stop at aldehydes. We are not concerned with studying all the different types of oxidants. So really, the point here for alcohol is that you can make an aldehyde from an alcohol. Know that first step. Alcohol plus oxidant makes aldehyde. You may, if you wish, then convert it onto carboxylic acid, which we'll discuss more in aldehyde reactions. Well, not only can alcohols become aldehydes, but remember the difference between aldehyde and ketone is position. So if I had propan-2-ol and I add an oxidant, well, it's going to do the same thing it did before. It's going to steal that hydrogen off the carbon and off the oxygen. It's going to force a bond between the carbon and the oxygen. It turned it into a double bond. But this time, because it was in the middle of a chain, it is a ketone. Ketones, if they see more oxidant, don't have a reaction. They do nothing. There are no more remaining adjacent hydrogens. I can't make any more bonds to that carbon. I'd have to break off other carbons. And so, because our carbon here only has other carbons still attached, there's nothing else to replace. Ketones will not go any farther. And so our alcohols can be converted to aldehydes or ketones by the addition of an oxidant, which we will put over the arrow because we're not concerned with what the actual species is. It is merely being used to convert our functional group for us. Alcohols can also form ethers. If I have an alcohol, in this case, I have 2 of them, they can react and form an ether plus water. Effectively, I have two OH groups. One of them displaces the other one. So this shoves that oxygen out. That oxygen leaves. It steals the hydrogen as it does it. And you end up with one oxygen bridging the two carbon chains, and the other oxygen that used to be an alcohol now turned into a water. This is also why most of our ethers have the same carbon chain. Diethyl ether, dimethyl ether. You very rarely actually have a methyl ethyl ether, because the only way to make a methyl ethyl ether would be to have methanol plus ethanol. They'd have to react. But if I have a big container that's half ethanol and half methanol, sometimes the ethanol bumps into each other. This would really give you a mix of dimethyl, diethyl, and methyl ethyl. You'd then have to spend the time to distill and separate them. It's actually very difficult to obtain mixed carbon group ethers, cost effectively. But if you just have a bottle of pure ethanol and you react it, then you end up with nothing but pure diethyl ether. This also requires heat, generally a little bit more heat and some acid. Compare this to dehydration, which is an alcohol plus heat. If you give it a little bit more heat and a little bit more acid, you can make these ethers. It's a problem, however, if you're trying to dehydrate an alcohol, you will accidentally make some ether. Both of them kind of occur at the same time. They are not clean reactions. Nonetheless, we can pretend they are for our purposes, and so if you want to make an ether, this is how you go about doing it. You just take the alcohol, and you apply heat and acid, and it will create your ether from the alcohols. In terms of alcohol reactions, there are a few others that we'll see when we talk about esters, but that is the functional groups alcohol themselves can convert into. So your alcohol, ROH, plus heat can become alkene plus water. Your alcohol plus heat can also become ethers plus water. Your alcohol plus oxidant can become aldehydes or ketones, depending on what your starting molecule is. And these are three of the general tools we have for alcohols: form alkenes, form ethers, form aldehydes or ketones.